In the previous lecture, we have started our second chapter of section 1 thermodynamics, and heading of the section 2 is the thermodynamics and quantum chemistry. So, first part is thermodynamics, and in which we will see second chapter, second of thermodynamics. And thus, we have already seen few points. In today's lecture, we will discuss the next points in same chapter. The entropy changes in the system, Clausius inequality, entropy changes for the reversible processes. These are the 3 points which we are going to discuss in today's lecture. So we will start with the entropy changes in the system. So our first point is this: the entropy changes in the system. So use the surroundings to restore the system to its initial state reversibly with no further generation of energy. So in the previous lecture we have seen definition of entropy as entropy is a measure of disorder. For example, we have taken water. Initially take ice. After providing heat to this, it is converted into liquid, and then again provide heat to the liquid, it will get converted into the vapors. That means solid, liquid and vapor states are there. As the interaction of the molecules is going to decrease, the system goes on increasing the entropy. So solid has a less entropy as compared to liquid, and liquid has a less entropy as compared to the gaseous state. So this is the measure of entropy, or the entropy is a measure of disorder simply. So in today's lecture we are going to see the how entropy changes in the system. So initially we have to take the surroundings to restore the system to its initial state reversibly with no further generation of energy. And then we have to inspect how much entropy has been transferred in the process. So, set the temperature of the system is equivalent to temperature of the surrounding. That means T is equal to T dash. T is the temperature of the system and T dash is the temperature of the surrounding. That means the system is in thermal equilibrium. Then heat transfer is reversible, and entropy changes is in between initial and final state, that is S2 and S1, but system is not reversible. Heat transfer is reversible, but system is not reversible, and entropy changes in between initial and final states. So entropy is a state function and the heat is a path function. Entropy depends on the initial and the final states, but Q does not depend on the initial and final state. That's why it is a path function. Then consider the system is restored reversibly to its initial state. Its entropy changes by minus ds. So change in entropy is written by minus ds when system is restored reversibly to its initial state. And for the forward step, the heat is also negative. That's why dq reversible is negative, or rate of change of heat is negative. Then when system works on the surrounding, or the surrounding work on the system. So initially we are going to take our first condition, surrounding works on the system. When surrounding works on the system, there is a compression and the heat is given by equation dq dash is equal to dq reversible. And then we are going to write down the entropy. Entropy's definition is ds is equal to dq reversible by t. That's why ds dash is equal to dq reversible by t. So total entropy change is given by equation delta S. Delta S represents the change in entropy of the initial and final states, and this can be given by equation integration of dq reversible by t. So integration will be from initial state to the final state, and now q is not a state function, that's why we cannot write as a q2 minus q1. So simply Equation remains as it is, only integration sign is removed. So delta S is equal to dq reversible by T. So this is our definition. Delta S represents the change in entropy of the system and surrounding, which is equal to dq reversible by T. Now the Clausius inequality. This is our next point of today's discussion. The Clausius inequality, it was shown using two examples that delta S is greater than 0, which provides the criteria to predict the natural direction of change in an isolated system, and this result can also be obtained without considering a specific process. Now consider the differential form of the first law of thermodynamics for a process in which only pressure volume work is possible, and du is equal to dq minus P external dV. Pex shows the external pressure, dV is the change in volume, dq is the change in heat, and du is the change in internal energy. This equation is derived from the first law of thermodynamics. Du is equal to dq minus P external into dV. This is our equation number first, and this equation can be written as du is equal to Tds minus P delta V. So this is the second equation. Because U is the internal energy and it is a state function, du is independent of the path, and above equation number 2 holds for both reversible and the irreversible processes, as long as there are no phase transitions or chemical reactions, and only pressure volume work occurs there. Next, to derive the Clausius inequality, we equate the expression for change in internal energy in equation 1 and 2. So, just take subtraction of equation number 2 to equation number 1. So, 2 minus 1. Therefore, equation can be written as dq reversible minus dq. So, this is the equation, and we are going to write down the subtraction as dq reversible minus dq is equal to p dv minus p external dv, which is equal to p minus pex, and take dv common. So, p minus p external in a bracket into dv. This is our equation. So, here du is equal to dq minus p external dv. This is our equation number 2. And here you can write du is equal to dq reversible dash. Instead of Tds you can write dq reversible. And here is the pdu. So just take subtraction and write down the equation as dq reversible minus dq is equal to p dv minus p external dv is equal to p minus p external in a bracket into dv. Suppose P minus P external, or the change in pressure, is nearly equal to 0 or greater than or equal to 0. System will spontaneously expand and the change in volume is greater than 0. And if P minus P external, that means change in pressure, is less than 0, or the difference between change in pressure is less than 0, system will continuously contract, and here sign is less than. So here I have written greater, but this is not the case. Here dV is less than 0. In first case, when system expands, dV is greater than 0, and when system contracts, obviously volume is going to decrease. That's why change in volume is less than 0. Then dq reversible minus dq is equal to Tds minus dq, which is greater than or equal to 0, or the case Tds is greater than dq. Now, equality holds only for irreversible processes. So, we can apply equality condition only for irreversible processes. So, consider this equation can be written as ds is greater than or equal to dq by t. So just transfer this t to the right side. ds is greater than or equal to dq by t for a reversible isothermal processes, and when change in heat is equal to 0 and entropy change is greater than equal to 0. This is the Clausius inequality. This equation is useful for Clausius inequality. And for an isothermal irreversible process in an isolated system, dq is equal to 0. Therefore, we have again proved that for any irreversible process in an isolated system, delta S is greater than 0. And the Clausius inequality is next used to evaluate the cyclic integration of dq by t for an arbitrary processes, because ds is equal to dq reversible by t and the value of the cyclic integral is 0 for a reversible process. And now we will see next point, entropy changes for irreversible processes. So consider the two cases, adiabatic process and the cyclic process. For adiabatic process, obviously change in heat is equal to 0 because heat is constant for adiabatic process, and delta S is equal to integration of dq reversible by t, which is equal to 0. And for second case also, for cyclic process, again change in entropy is equal to 0, because change in any state function for a cyclic process is equal to 0. And now the third case is, now consider isothermal expansion or compression of an ideal gas when system changes from Vi, that is initial volume and temperature is Ti, to Vf Tf. So Vf and Tf shows the final volume and the temperature. And now temperature is the constant, then obviously change in internal energy is equal to 0. And when change in internal energy is equal to 0, first law of thermodynamics can be written as Q reversible is equal to minus W, and W is equal to nRT ln of Vf upon Vi. This is our equation when change in volume is there. And our definition of a change in entropy is delta S is equal to dq by T. This can be written as, just put Q is equal to nRT ln of Vf upon Vi. So just I have written here nRT ln of Vf upon Vi, and this 1 upon T is as it is here. So this 1 upon T and here multiplication in this, there is a T. So this T and T get cancelled. So equation of change in entropy delta S is equal to nR ln of Vf upon Vi. So this is our entropy change for irreversible processes. So we can say when delta S is greater than 0, that is the expansion. That means change in entropy is greater than 0, system will expand, and when delta S is less than 0, system will undergo compression. So this is all about the entropy and the second law of thermodynamics. Now consider delta S for an ideal gas which undergoes reversible change in temperature T at a constant volume or the constant pressure. So one thing will be constant, either pressure or volume. So system will changes from VI-Ti to VI-Tf. Volume remains constant and only temperature is changing. Ti to Tf. Volume is as it is Vi. So dq reversible is equal to N into Cv into dt. Here Cv represents molar heat capacity at constant volume, or the heat capacity at constant volume. So delta S is equal to N into Cv, integration of dt upon T. So N into Cv as it is ln of Tf upon Ti. So this is the entropy change when system undergoes reversible changes, and the temperature is changing and volume is constant. And for irreversible processes, when pressure is constant, means pressure does not changing, PITI to PITF, only temperature is changing. So dq irreversible is equal to N CPm into dt. So CPm represents molar heat capacity at constant pressure. N is equal to number of moles and dt is the change in temperature. So according to definition, delta S is equal to dq irreversible by T. Just put value of dq irreversible here and the equation became delta S is equal to N into Cpm integration of dt upon T. So delta S is equal to N Cpm into ln of T upon Tm. So this is the equation for the reversible processes or the system and surroundings. There is either expansion or compression. You can find out the entropy change by using this equation when you know molar heat capacity. So when pressure is constant and temperature is changing, the equation of change in entropy is equal to N Cpm into ln of T upon Ti.